So I hope everyone enjoyed the Super Bowl halftime show yesterday. I speak Spanish, but I did not understand what he said either, so we're all safe. Anyway, welcome to the AstroAI seminar, and today I'm very happy to host Ming-Shau Liu from the Flatiron Institute. He is currently there as a visiting researcher. Ming-Shau got his undergrad from the University of Cambridge in the UK, and he's been spending some time in New York. He also came for the AstroAI workshop, I believe, in the summer, and we met in San Diego in December, where he gave a very nice spotlight talk on his research that he's been doing with Carol on simulation-based inference for cosmology, in particular on capturing, feedback from baryonic matter, across different simulations. So that's what he's going to be telling us today. And so the floor is yours. I encourage you, as always, to interact with questions, and I encourage discussion. Other than that, it's all yours. Thank you.
Well, yeah, thank you, Rafael. I think we met.
Sorry. I should say, please remember to fill in this thing so that we can keep getting the food. Thanks.
Yeah, thank you, Rafael. I think we met when the weather was a lot nicer.
Oh yeah.
Yeah, San Diego was lovely. Making simulation is really hard, as it turns out. If you're trying to simulate the whole universe, as most people in this room will figure out, is that because the structure on a small scale really affects what you see on a big scale. So in this system where like scale is highly coupled, it's almost impossible to get things exactly right if you're trying to simulate with a finite resolution. And here we have a pretty picture of ego simulation, which demonstrates that if you focus on like dark matter only simulation, which is gravity only, or if you think about n-body, and then hopefully we assume some sort of astrophysical feedback, or if you think about it, just like some sort of physics that translate from a gravity-driven only simulation to one that involves baryons. So here we have an example of the gas density. So if I want to learn something real about the universe from any of these observations, then what I really need is to basically look at this and be like, okay, does my universe look like this? If it does, can we do any inference on it? And so if we think back to the pipeline of doing a simulation-based inference, we have some observation. We want to compare to a simulation that we made with some physics assumptions. And by the way, please interrupt me on any point during the talk. I really hope this is more of a discussion. My talk is very short. So if you make your simulation with some sort of physics assumptions, and you try to infer cosmological parameters, so the question becomes like, okay, sure, if we want to learn something about gravity only dark matter, then we need to be more certain about what's going on in the hydro simulation, the baryonic feedback. And so what's the trouble here? The trouble is that, so this is from the Campbell's simulation suites. We see that like the state-of-the-art hydrodynamic simulations, we have here 8 examples, and they very quickly diverged. And the issue is that they start with the same cosmology and the same seed, but they disagree. They have large disparity. So if I want to do any inference, then that creates a problem, because what you infer depends on the type of hydrosims you're choosing. So the idea we're proposing is we summarize this into a unified continuous latent space, and where within this latent space, around the order of 10 dimension, we'll have one corner that sits illustrious TNG, one corner that sits Simba, one corner that sits Astrid, and within each of those corners, they're each going to have their own astrophysical feedback.
So what is the input data for each of these for this Disney visualization? What was the input?
Next slide. You good. Okay, we can jump ahead basically. So we start with gravity only simulations. We want to see if we can predict baryonic feedbacks. But usually when you do this, what you're capturing is the probability of baryonic deltas given your gravitational deltas. But that's simulation dependent. So we want to do that across all simulations. So we want to calculate this space. How do we do it? So we start from gravity-only simulation, and then we have a generating model that sends it to the baryonic space. So for example, you can take a pick, whatever field you feel like. If you want the gas field, if you want temperature, if you want electron density, it really depends on what kind of observation you're interested in, right? But what this is really capturing is the probability of given a singular simulations of a baryonic fields of your choosing, depending on cosmology, that's the curly C. And by the way, we're using flow matching in this case. The good thing is that it performs a lot better on smaller scale features, and also the stochasticity really allows us to interpolate within the latent space that we're learning. But in order to get rid of that simulation, we add a ResNet bottleneck. What it does is it compresses baryonic information. Hopefully, an information bottleneck is enough to compress the necessary baryonic information that allow us to reconstruct the baryonic fields from gravity-only simulations. And we condition a Z bar onto this probability. So now this Z bar hopefully becomes continuous if we train properly, if we train across all the different simulations. Any questions so far? Okay. Yeah. And so here I'm going to show an example where we trained it over 4 different simulations. So we're training it over the TNG, Eagle, Simba, Asterisk. And here we're taking sets from the Latin hypercube sets from the Camel simulation, even though they both have about 6 parameters varying, 2 from cosmology, 4 from astrophysics, but they're defined differently depending on the kind of simulation you're using. And that's another key fact is that even if you can choose the same number of parameters that you're varying, they don't necessarily have the same physics. And most of the time when we go to larger simulations, they don't have the same number of parameters as well. And so the choice of that information bottleneck becomes very key parameter we have to tune in order to get a good summary from the different aspects of feedbacks. And so, for example, here in each panels, I'm highlighting the ASN1 for each of the simulations. And you can see like it captures some trend within each simulation, even though they represent different physical constants. And so here are 3 things we can try to do to test it. So first thing we can do is that we can try to reconstruct baryonic hydrogen simulations from gravity-only simulations. So if my model is trained on TNG, and we choose these 4 corresponding fields, and sure, we can reconstruct it like the model has seen before. But what's really interesting is that if we take magneticum, which is a held-out simulation that the model hasn't seen before, we can also achieve a pretty good performance. So this is like a 0-shot emulator, right? Like the model has never seen hydrogens from magneticum before. It doesn't have the same physics, doesn't have the same subgrid prescription, and it probably doesn't even have the same number of parameters. But if we condition it on the map compressed from the baryonic fields, we can still have good enough reconstruction. Are there any questions so far? So we can, the classic test we can do is to look at the cross correlations between them, and where one is more accurate. So y-axis is more accurate than the x-axis. When you go higher is the smaller details. So we see deprecation on a smaller scale, sure. And that has to do with the capacity limit of the model. And if we do across it, sure, like the gas temperature is worse. And one thing that we really want to compare is that the amount of information that's being reconstructed in the temperature is associated with the correlation between the dark matter and temperature map. And so there are very different. And so we see that, okay, that's something we need to improve on. But also, like the real design question is how many fields do we really need to get a good understanding of the astrophysical data that we really care about? And another thing we can do is interpolation. So previously, you might say that, okay, let's pick some point in asteroid, and let's pick some point in eagle, which is previously two completely different simulations. But now we can make statements like what's 80% eagle and 20% Simba, or 20% asteroid in this case. So here we have, within the latent space, we have a linear path that goes from this one point to the other, which I chose specifically to have the same seed to demonstrate that the model is capturing the smooth transition between the two baryonic feedback mechanism. So the linear path is the linear path in AD, so it's not really a linear path in the t-SNE projection. And along this path, you can see that it captures the correct behavior in temperature and in gas, and in pressure in stars in this case. Questions? So now we can say that what's if I have some initial condition, if I have some n-body simulation, I can ask, okay, what does it look like if it's somewhere between asteroid and Simba, which is completely different physics, right? And different number of parameters.
So maybe I'll
Sure.
I'll use this. So you're showing us that your generative model has been trained on illustrious data, but you can accurately predict for other simulations on which you have not.
No,
is that a true statement?
So it was trained on 3 different simulations.
Okay.
Sorry, 4. It's trained on TNG, asteroid, Simba, and eagle.
Okay.
And because the stochasticity from the flow matching model, which we inject noise at x naught, which by the way is because the flow matching model, it predicts the velocity map that transport between the 2 probability distributions. It's able to reconstruct magnetic count, which you asked in before.
Okay. And so the fact that all those different simulations live in different regions of this representation space that you're showing in t-SNE, that you can still sort of predict for the magnetic with certain accuracy. Does that mean that there is like some sort of one-to-one correlation in that space? You could align those spaces for the different simulations. Is that try to okay? That's
the idea. So the different hydrosim, different subgrid physics, which is typically very discrete. I mean, from camels we have 8, sure, but they have very different descriptions. But now the description can be captured with one variable in one latent space.
Got it. Thank you. Any other questions?
A quick question. You might have explained this already, but could you remind me why you chose, or why is there 8 dimensions for the embedding space?
So that is a parameter we have to tune. So there's a lower limit to it, which is for most of these simulations, like there's at least 4 astrophysical parameters. So we should have at least 4. And on the upwards, in some simulations, there's 28 to 35 astrophysical parameters. But if it's too big, then the stochasticity doesn't really cover the interpolation region. So it has to be small enough that the information bottleneck still compresses enough shared information that the latent space is useful. And 8 is like the first non-trivial number of dimension, well, by factor of 2. But we can explore upwards. So in the new simulations from camels, which in second generation is 15 megapulsar boxes, and they're distributed on the Sobol set, Sobol 35, that's 33 parameters. And also there's more simulations, right? There's crocodile, there's obsidian, there's Ramesses, and we might have to explore the number of parameters in that. For this particular mod working example I'm showing, like 8 was a number of that worked.
Yep.
This is very nice work. I was wondering about the computation time
Sure.
for what you do compared to these simulations?
Yeah. So to generate one simulation, okay, I'm gonna skip ahead. So to generate one simulation, it takes about 6,000 CPU hours to do a hydrosims. So this is effectively an emulator, right? And this emulator takes about 5 GPU minutes to generate a one-way convergence. But there's a caveat to it because it's built on a flow matching model, which is stochastic in nature. And so a number of sampling steps you have in your flow matching time matters. So it can range just from a few minutes to 10 minutes, depending on like how fine you want your model to be and what you really care about. But generally, it's on the order of millions of GPU minutes. And as for training, that's another thing I really care about as well. Because I really want to be able to just train on one GPU. And one GPU, right now we're training on A100's 80 gigabytes. I'll make sure I can use H200. But if I really want people to use this, I have to limit my usage. So the model, we really have like sort of resource constraints in mind as well. And right now I can train on one 80 gigabytes GPU for about 3 days on the A100. It converges, and it sort of scales linearly with the number of simulations we want to consider. And the fine-tuning for the information bottlenecks and other thing. But the reason why we do this is because once you have a continuous latent space, what we can do is, so each of these points in this space, I can say, give me an initial condition. I can make you new emulation of this simulation, right? I can do SPI on those maps and say, okay, let's say within this space, I make electron density map, these electron density compressions on this latent space across the different simulations. I can make mocks of, say, fast radial burst, and I can compare that to my observations. I can infer where it lies within a latent space. So what this can tell me is across different hydrosims, are there shared features, like are there redundant features, and what features really matters? And if we can fill out this space with synthetic simulations, then that also allows me to train an inference model that hopefully, if it improves, that means that we don't need to make new hydrosims. But if it turns out that it doesn't improve, then that points to us that what kind of hydrosims we need to make in the future. Whereas right now, the exploration of the subgrid physics description is sort of based on expert experiences, but now we can take a more observation and data-driven approach to designing these hydrosims, right? Yeah. So to go back, so this plot is really to demonstrate that the space is continuous. It's not blotching. So if you think about it, like sure, it looks like there's lots of pointing here, but this is an 8-dimensional space. And in high-dimensional spaces, your information is extremely sparse. And across this like mostly void spaces, which by the way, as you can see from the gaps within the simulations, because we give the model all the information it needs. This is an extremely sparse space. They are extremely separated, but somehow it's still able to recover a good quality hydro simulation maps, and something that's even captures the trend of the different feedback parameters. And so obviously another thing we need to test is within each simulation, which has its own varying astrophysical parameters, it should still be able to capture their particular features. So for example, if I vary particular wind energy, which in a CAMOS data set, it gives you, I think, 5 values within 1P, 1 parameter varying. And within that range, I can have a I can move continuous across that space and capture the difference that particular astrophysical parameter changes. And I can also do that with Simba, and I can do that with abstract. So it's really one parameter that works across the field, and on the field level as well. So the reconstruction quality is checked on field level, which we want to do for SPI. instead of just a summary statistics style emulator. And so here are some future directions that we're currently thinking about. So if I take a 25 megaparsec boxes, I give it all information about the embodied simulations. Well, I'm picking map density and velocity of dark matter. I can create a flow matching that gives me a gas NE and T field. And this is just to show the averaged. So the stochasticity is important here because especially in things like temperature where I want to do marginalization. But for each of these, I can make different mocks. For example, in the density, I can make fast radial bears. In temperature, I can make T as Z. And also, another thing we can do, this is a fully convolutional model, so we can do upscale reconstruction. So what this means is that I can train my baseline model on 25 megaparsec boxes. And from embodied simulations of 50 megaparsec boxes, I can generate baryonic feedback for that particular scale, for like 50 megaparsec. And so this is again, this is like a zero-shot kind of predictions because the model hasn't tried it before. And this is one example I generated. That's pretty good group. So the cosmology is not matched here, so it's not perfectly matched. But as you can see that, for example, the cross correlation, like for 25 megaparsecs, it stops at a certain point, but it's able to reconstruct the large scale structure and a blue tail here as well on the larger scale features. And in the gas, in the power spectrum as well, we have good matching between the two power spectrum. So there's two directions to this work currently. So we created this model that's able to capture the robustness of between different hydrogens, creates a continuous space that allows to do marginalization and allows to do inference, to make better hydrogens in the future. And at the same time, this model architecture allows us to upscale embodied simulation, hydrogen simulation from relatively cheaper and good embodied simulation. And as we found out actually, the quality of the embodied simulation matters a lot. So we also train similar models for particle mesh. And we're trying to find sort of like the limit at which the particle mesh inference breaks down. And so right now what we found is that we really need like an embodied resolution for this to work. But yeah, some future work. So we have the examples I've shown you are in 2D. Well, they're easier to visualize, but we do have 3D models working in both 25 megaparsec boxes, 128 resolution, 256 resolution on 50 megaparsec boxes as well, which we can do by training on smaller boxes. We can do the robustness. One thing that Camel's illustrated importantly is that if you train inference on one hydro simulation, it's very difficult for it to work across different simulations. But what we can do is on the latent space that we encode, we can create Gaussian envelopes that fill the space, and we can resample within the space to create more simulation that train our models on. And that's hopefully we'll be able to solve the inference problem within Camels. So you can marginalize across astrophysics of different descriptions. Another thing is that we can draw prior, train the simulation robust inference. We learn about baryonic feedback, the inference about from observation is what I talked about, essentially mentioned about making better hydrogens. So from the fields that we create, we can make mocks. From those mocks, we can compare that either through summary statistics or through field level inference of actual observation data, feed that back into a Z-bar space. And sure, that's one caveat is that the Z-bar, it does capture physical information, but maybe not in a practical way. But from this, maybe we can use the vicinity search within the latent space to figure out what physics really matters for future hydrosims. But yeah, that's the work. Carry out that Flatiron and I find questions.
Thank you, Ming-Shau. Very nice talk. Any questions, Ming-Shau? Yes.
Is there any sort of consideration of physical properties of these output emulator things like total masses of the boxes should conserve mass or momentum or anything like this? Or are you just emulating from what you start with?
So I emulate with what I start with, and we don't sort of constrain it by hand with the summary statistics. But the ultimate test that we're doing and is currently passing is the inference test. So I create essentially this like say gas mass mocks. If I build an inference model on that to predict the astrophysical parameters or predict cosmology parameters, it's an even bigger challenge for my mocks to have to matches that and get the same inference result as well. And that's the bench that we're setting for the quality of these mocks. And the ultimate test is for the upscaling. We get a 50 mocks at boxes. So 0 shot, go from 25 directly, get embodied, choose up to 50 baryonic hydrosims. And if that passes the inference test as well, then we're pretty happy. And right now, Camel's at 300 bucks, and that's our goal. Because that would be pretty cool. And with some repeated boundary conditions, maybe we can make Desi scale. And that's far in the future. But to answer your question, inference tests is what we really care about. And I think that's the most stringent test in some statistics.
Questions, comments? So could you tell us a little bit about the your plan to incorporate the observations? So one thing that you did mention was the TSE effect.
Yeah.
And so what exactly would be the so the procedure here? Is that a framework in which you would condition your trained model on particular observations that you have? And if that's the case, what sort of observations of the TSE effect would you need for that?
Well, particular model training, we wouldn't conditioning on the observations. The idea is more like so if the model is trained in a completely unsupervised way, it's essentially a foundation model, right? Like we have an information bottleneck, it compresses it, and all that tasks I talk about, reconstruction, interpolation, extrapolation, they're all like additional downstream tasks that we provide. But so it's a foundation model in a completely unsupervised way. And so we will get the latent space. But what we will do is that within that latent space, we're going to create synthetic mobs and regions where it matters. So we can make those mobs and we can fill that space. And that means that we can, if we can create mobs from those space, then we essentially have a mapping from the latent space to say PIZ map space or FRB map space. And then we can marginalize over that. Sorry, not marginalize. We can see sort of where the observation lies within the space. And what we're really interested in is that maybe there are some parameters in hydrosims that they are degenerate with each other. And can we figure that out? And are there similar astrophysical feedback that mimic each other? Like there's a very big space to figure it out, and the observation will help us pinpoint on exactly which space we should be working on and figure out the physics that region, because that would be place sort of where we should where it really matters and where we should do most of our work to improve hydrosims. So the observation is more to guide us within this latent space of where we should explore.
All right, thanks.
And of course, do SDIs and do much more like over the synthetic space.
All right, well, it looks like people are still thinking hard about the implications of your work. Ming-Shau will be around until Wednesday, and he'll be sitting in 3 or 4 in the B side of the building, in case you guys want to chat. Happy to arrange for discussions. Other than that, let's thank him again for nice talk. Thank you. It's a holiday next week, so there's no talk. We'll see you in 2 weeks.